All right, a little late hitting the recording button, but we're partway through the first question, so I didn't miss too much. We're going to pick experiment 3 to solve for K. And we would say here that K is equal to rate divided by concentration of NO squared divided by concentration of Cl2. And that's just a rearrangement of that equation up here. And so our rate for experiment 3 is 9.59 molarity per hour. Our concentration is 1.00 molar squared, 1.00 molar. And this gives us a value of 9.59 molarity to the -2 seconds to the -1. Not seconds, hours to the -1. So I guess if you wanted to write out the entire rate law for this reaction, it's just going to be rate is equal to 9.59 molarity to the -2 hour to the -1 times concentration of NO squared concentration of Cl2. All right, so states of matter aren't given here, but this is a gas phase reaction. If you have a gas phase reaction like this, you can use pressures instead of concentrations. The only difference is that your value of K will not be in units of molar anymore, it'll be in units of bar or some other unit of pressure. Cool. So we can move to the next question. This is using the integrated rate laws, and it says a first order reaction A goes to B, is 25% complete in 42 minutes at 25 degrees Celsius. What is the half-life of this reaction? So in order to get half-life, what we really need to get is K, because half-life, T1/2, is just the natural log of 2 over K. So if we have K, we have half-life for a first order reaction. And the integrated rate law for a first order reaction is A at time T is equal to the initial, shouldn't say A, let's say concentration of A at time T is equal to the concentration of A naught, meaning the initial concentration of your starting material, times e to the minus kt. So what we can actually do is rearrange that equation to express it in terms of K. So if we take the natural log of each side, we get natural log of AT equals natural log of A0 minus KT. And then if you rearrange in terms of K, you get the equation K is equal to the minus natural log of A over A0 concentration, all divided by time. So that's just a rearrangement of that integrated rate law. You can do this different ways. What I like to do, if it's simple, is rearrange the equation in terms of the variable that I'm trying to get, put all the numbers in and calculate in one shot. You can actually use the initial form of the equation, fill in the numbers you want, do a little bit of mathematical manipulation before rearranging, whatever you'd like to do. So up top here, we have this A over A0. We don't actually have concentrations at time t or initial concentrations at all. But what we do know is that it's 25% complete after 42 minutes. So if it's 25% complete, that means that there is 75% remaining. And what we can say then is that A at time t over A naught equals 0.75, right? So this just becomes negative natural log of 0.75, divided by 42 minutes, and that equals 6.85 times 10 to the minus 3 minutes to the minus 1. That's K. We're good. We have units of time to the -1, which is great because this is a first order reaction. So these are the correct units. And now we want to find out T1/2. Ln 2 over K equals ln 2 over 6.85 times 10 to the minus 3 min to the minus 1. And that's going to work out to 101 minutes. Which I guess really what we should say here, that's 3 sig figs. We should really only have properly 2 sig figs. So we could just say like 1.0 times 10 to the 2 minutes. But I'm not going to be super fussy on sig figs, unless you get ridiculous. Like if you gave me 6 places after the decimal here, then yeah, I don't want to see that, but this is good. The next one is a sort of a non-mathematical one. It's giving you the mechanism, a 3-step mechanism for this reaction of hydrogen peroxide with iodide and H plus. And you can see there's 3 separate steps. If you add those 3 steps together and cancel what appears on both sides, then you should get the overall balanced equation. And you see the first step is slow, second step is fast, third step is fast. It says identify all intermediates in this mechanism. So an intermediate is something that is generated in an early step, consumed later on, does not appear in the overall balanced equation. So we have the overall balanced equation right here. Basically what we can do is look down below for what appears in there that's not in the balanced equation. Just one thing I wanted to mention about all of these questions is it seems to have kind of screwed up the superscript a little bit. I don't know why, but it seems like things that were superscripted have come down. Like you can see that here, for example, like that H plus, it should be superscript plus, not subscript or whatever that is. What it seemed to have done is taken all the superscripts and made them subscripts. So anyway, if we know what it is to be, we're good. So in the first step, we have H2O2 reacting with I minus, both are in the balanced equation, producing HOI and OH minus. Neither of those appear in the balanced equation. So an intermediate would be something like HOI, OH minus. Second step, OH minus plus H plus makes water. H plus and water are both in the balanced equation, so they're not intermediates. Finally, in the last step, the HOI that we produced early on reacts with the H plus and the I minus to make I2 and H2O, again, both in the balanced equation. So these are the only 2 intermediates in this particular reaction. What would be the rate law for this reaction? Well, you can't tell from the balanced overall equation, but you can, because we know the mechanism, we know the first step is going to be the rate determining step. So we could say that rate is going to be equal to K times concentration of H2O2 I minus. So we would say this reaction is going to be second order. We would use a second order integrated rate laws. That's that. One more. The peroxodisulfate ion can oxidize iodide ions to iodine according to the balanced equation below. The reaction is catalyzed by a certain chemical species. Identify the catalyst. So actually, this is not the last one, but this is basically looking for the catalyst, and the catalyst is something that's present initially, present at the end, is used in the reaction, but is regenerated. So it does not appear, well, it technically does not appear in the overall balanced equation because it's not a reactant or a product, but it is certainly present. So here we see Fe3 plus reacting with 2I minus. The catalyst is sort of the opposite of an intermediate. It's present in an early step and gets consumed, but then gets regenerated in a later step? The answer is going to be Fe3 plus. It's consumed in the first step, does not appear in the balanced overall equation, and it's regenerated in a later step. Cool. When acetaldehyde at a pressure of 364 millimeters of mercury is introduced into an evacuated 500 ml flask at 518 degrees C, the half-life for the decomposition process is 410 seconds. Now, this is second order, right? What will the total pressure in the flask be after 1 hour? Okay, well, first of all, what we can say is that the half-life, the equation for a second order process, is 1 over K times initial concentration, or in this case, because we're dealing with gases, initial pressure. Pressure is obviously proportional to concentration using PV equals nRT. Okay, so that's good. We have initial pressure, which is that, and we have T1 half, which is 410 seconds. So what we can do is solve for K. K is going to be equal to 1 over T1 half P0, 1 over 410 seconds times 364 millimeters of mercury. And that's going to give us 6.70 times 10 to the minus 6 millimeters of mercury to the minus 1 seconds to the minus 1. So we have units of concentration to the -1, units of time to the -1. This makes sense for a second order decomposition. Great. So now what we want to do is figure out what the total pressure in the flask will be after 1 hour. So we know what the initial pressure is of our reactant. What we want to do is find out the final pressure of our reactant. So what we can say then is that the pressure, well, we're going to use our integrated rate law, which is 1 over pressure at time t is 1 over initial pressure plus kT. And if we rearrange that to express it in terms of just our final pressure, 1 over 1 over P0 plus KT. We just took the reciprocal of both sides here. And we've got all our numbers. Let's put them in. 1 over initial pressure, 364 millimeters of mercury, plus K is 6.70 times 10 to the minus 6 millimeters of mercury to the minus 1 seconds to minus 1. It's going to be a long one here. And we want 1 hour. So we need to convert hours to seconds. There are 3,600 seconds in 1 hour. And when we run that calculation, we end up with 37 millimeters of mercury. Now, this question I've given to it people before, and people always like put 37 down as their answer, and then they get it wrong because they didn't clearly read what the question's actually asking. Question doesn't want to know what the final pressure of that reactant is, of the acetaldehyde. It wants the total pressure in the flask. So what's happening here is you have CH3, CHO, which is a gas, reacting to make CH4 gas plus CO gas. And if you think of it like an ice, right? Initially, we have 364 millimeters of mercury, 0 and 0. Final is 37 millimeters of mercury. It's going to produce CH4 and CO, which are both gases, and both add to the total pressure. So the change here is minus 327. 364 minus 327 is our 37 millimeters of mercury. So that means over on this product side, we have plus 327 and plus 327. So 327. So our pressure total is then the sum, so it's going to be 37 plus 327 plus 327 equals 691. A little bit tricky, a little bit of an extra twist at the end of that one, but we're using, again, just our integrated rate law. We need K, we need initial concentration, and then we can just go from there. So hopefully this makes some sense. We're going to jump into the next chapter, and this was the first thermochem chapter, and the chapter, arguably, I guess you could say, is mostly about delta H, the first law, thermodynamics, and we looked at lots of different ways to solve for delta H for a particular reaction. I want to double check the chat that everyone's happy. It's like everyone is. This question says the heat of solution, and this has got some old language in it because now we call that enthalpy. The enthalpy of solution of ammonium nitrate is 26.2 kilojoules per mole. If a 3.68 sample of ammonium nitrate is added to water in a calorimeter, what's the minimum temperature reached by the solution? So you can see that the enthalpy of solution is a positive value. That means it's endothermic. That means it's going to cool down the system when it's placed in and it's going to dissolve. And we know how much energy is absorbed per mole, and we know how many grams are there. So we can actually figure out exactly how many joules of energy would be absorbed by this thing dissolving. So first of all, we need the number of moles, mass over molar mass, and that's 5.368 grams over the molar mass of ammonium nitrate, which is 80.043 grams per mole, 0.06706 moles. Okay, so Q of this reaction is going to just be equal to the delta H times N, which is 26.2 kilojoules per mole times 0.0676706 moles. Almost ran out of space. Arguably, I did run out of space. And that equals 1.76 kilojoules, which is 1760 joules. Great, so that's how much energy is absorbed by this particular chemical step. So this is happening inside of a calorimeter that contains 40 mils of water, and its starting temperature is 23.5. So it's asking, what is the minimum temperature reached? So how much would this cool down by under ideal conditions? And it's giving us the specific heat of water and the heat capacity of the calorimeter itself. So really, what's going to be happening here is we have some of this energy that's going into the reaction is coming from the calorimeter itself, and some is coming from the water that's in the calorimeter. So you see this three different ways. Sometimes the water is included in the heat capacity of the calorimeter. Sometimes we only worry about the water, and sometimes we have to worry about them both. So this is a situation where we worry about them both. So what we can say then is that Q equals M well, it's C delta T. And this C actually has two pieces. It has the calorimeter heat capacity, and it has the heat capacity of the water that's present in there. So what we can say is this is the C of the calorimeter plus CS, the mass of water, times the specific heat capacity of water, times delta T. So this gives us kind of our two pieces. What we're really interested here in is our delta T. Delta T is going to be equal to C cal plus MCS over Q. And our values for up top are going to be equal to, I got that the wrong way around, don't I? Yeah. Delta T is equal to Q divided by C cal plus MCS. Now, the Q for the cal is going to be opposite the Q of the system, because everything the system absorbs is lost by the calorimeter itself. So we put a negative there because this is like the Q of the calorimeter. This was the Q of the system. So now we put in the capital C for the calorimeter, which is 650 joules per degree C, plus the mass of water is 40.0 grams, assuming a density of 1, 4.18 joules per gram degree C. And this gives us a value of negative 2.1 degrees Celsius. If you look at our units, the joules will cancel, the grams will cancel, and we're just left with degrees C. So our T final is just going to be our initial temperature, which was 23.5 degrees C, minus 2.1 degrees C, and that equals 21.4 degrees Celsius. So just always in these kinds of problems, it's easy to lose a negative or like, you know, flip the sign accidentally at some point. Just try, in my mind, I don't like to memorize the formula. What I like to think about what's happening in each particular step. So if you think about this substance, it's endothermic. The temperature is going to go down. It's going to absorb energy. If you end up with an answer that increases your temperature of your calorimeter, you know you messed up a negative sign at some point, because it's got to go down. You got to lose heat. You got to decrease the temperature. Great. Next one, ethanol undergoes combustion in oxygen to produce CO2 in liquid water. Standard heat of combustion is blah, blah, blah. So this is figuring out the delta H for a combustion reaction using heats of formation or enthalpies of formation. So this is a different way that you can calculate delta H for a reaction. We talked about using calorimetry. If you can find enthalpies of formation values for everything in your reaction, you're doing well. So before we do anything, what we have to do is write a balanced equation for this combustion. We're starting out with C2H5OH, liquid. And combustion always kind of looks the same. It's reacting with O2 gas to make CO2 gas and H2O gas. Depending on the temperature, actually, you can get H2O liquid. Let's use liquid here because that's what they gave us the value for. Okay, so what we need to do is balance this. We need to put a 2 in front of the CO2 to balance the carbons. For the H2O, we need to put a 3. And for the O2, that results in 3 oxygens. So this should be our balanced equation. And looking at our delta H's of formation for everything we have here, we are given negative 1366.8 kilojoules per mole. We know oxygen is going to be 0 because it's a pure element in its standard state. It's a gas. The other ones are provided for us. Negative 393.5 kilojoules per mole. And for water, we have negative 285.8 kilojoules per mole. So this is pretty straightforward. Our delta, let's put a C there for combustion. Sum of the delta, not FH, of the products, minus the sum of the enthalpies of formation reactants equals, start with the products, 2 times negative 393.5 kilojoules per mole, plus 3 times negative 285.8 kilojoules per mole, minus, on the reactant side, just negative 1366.8 kilojoules per mole. And calculate that out, you get negative 277.6 kilojoules per mole. So we have a negative delta H. This is exothermic. This makes sense if you are doing a combustion. These are pretty straightforward. I mean, you just multiply them through, make sure you pick the right values, make sure that the numbers that you have here are for the correct state of matter you're dealing with. And that's it. Oh, you're right, aren't you there? The standard heat of combustion of ethanol. Okay, so, all right, so what we need to do here is say negative 1366.8 kilojoules per mole equals 2 times negative 393.5 kilojoules per mole plus 3 times negative 285.8 kilojoules per mole minus delta H of formation of ethanol. So yeah, you're right. I did that wrong. It doesn't actually, so the answer is correct. I went through the steps wrong there. Sorry about that. You're right. It would change the answer if you actually ran those numbers that I gave you here. But yeah, so this is the correct way. Thank you for the correction. Good. Now we're moving into the next chapter where we spent a lot of time talking about entropy, and we looked at standard molar entropies. Here are question 1, 5 substances, and it's asking which species is going to have the highest standard molar entropy, S0, at 25 degrees Celsius. And, you know, we're given methanol, carbon monoxide, magnesium carbonate, water, nickel. And really what you should be looking for here is what phase is it in. You're always going to have a higher standard molar entropy for something that's a gas. So right away, I would pick that one out as the only gas here. Solids and liquids, like liquids have higher standard molar entropies than solids, but they're a lot closer together than gases. Gases are way higher. The next question says, which of the following has the highest delta S? Which has the lowest? And what we look for first in questions like this is how many moles of gas are formed. So we look for delta N. In the first case, we are going from 2 moles of gas, CH4 and H2O, to CO and 3H2. So we're going to 4 moles of gas from 2. So delta N is +2. The next one, we have 1 mole of gas on the left, going to 1 mole of gas on the right. And the next one, we have 0 moles of gas going to 0.5 moles of gas. So we would expect the highest delta S to be the first one. It's producing the most gas. And the second one would be the lowest because it's producing the least. And then the third one would be somewhere in between. That's all we're really looking for in these examples, just how much gas gets produced. Next question says, ozone in the atmosphere can react with nitric oxide. This was the source of a Nobel Prize, this reaction. In 1995, the Nobel Prize was given, and it went to, his name was Paul Crutzen. And him with 2 others determined that in addition to this reaction, there's other reactions which cause ozone depletion in the stratosphere, and they're responsible for depletion of the ozone layer, and they managed to figure out the source and managed to then, which led to a solution. So we've fixed that particular problem. Calculate the delta G0 for this reaction at 25 degrees Celsius, given delta H and delta S. So this one is actually very straightforward. This is just using the Gibbs equation. Just that. We're given all of the numbers we need to calculate here. I guess the only tricky part here is making sure your units of delta H and delta S go with each other. And right now they're not. One is in kilojoules and one's in joules. So we can just make delta H negative 199,000 joules per mole minus the temperature is 298 K or 25 degrees Celsius, negative 4.1 joules per K mole. And that gives you negative 198 joules per mole, which is negative 198 kilojoules per mole. It's very interesting in this case how small an impact the delta S has on the overall delta G. This delta is hugely dominated by the delta H value, right? The whole T delta S part barely had an effect, which I guess sort of makes sense if you look at the balanced equation, because our delta N here is 0. No change in moles of gas. So we expect delta S to be a small number, close to 0, and therefore not to have a large impact on the delta G of the reaction, which is exactly what we see. It changed it by 0.5%. Sodium carbonate can be made by heating, sodium bicarbonate, according to the balanced equation that you see there. Given that delta H is that number and delta G is that number, what minimum temperature will the reaction become spontaneous under standard? Above what minimum temperature will the reaction become spontaneous under standard state conditions? Okay. Well, we have delta H0 and delta G0. I think what we're missing here is delta S0, which we can calculate from the other two. And that little 0 means under standard conditions. Everything's 1 molar. If it's gas, it's 1 bar, 25 degrees Celsius. And we need to calculate for delta S. So what we can say is that rearranging this, we can say that T delta S0 is delta H0 minus delta G0, and that delta S0 is delta H0 minus delta G0 over T equals 128,900 joules per mole minus 33100 joules per mole divided by our temperature, which is 298 K, which ends up giving us 321.5 joules per K mole. Now, that's a big number, isn't it? 321 compared to, our question on the previous slide, which only had -4, very small number. So we're like, 100 times bigger than that. And that makes sense because look at our reaction. We're producing gas. Our delta N here equals +2. So if we're producing gas, we expect a bigger delta S, positive delta S, which is what we see. All right, so we have our delta S0, and when we get a reaction like this, we need to make the assumption that the delta S0 and the delta H0 don't change a lot when you change the temperature. So what we need to do is calculate the delta G under the non-standard conditions, and we need delta G to be equal to 0. Because delta G equals 0 is the point at which a reaction switches from becoming spontaneous to non-spontaneous. So what we need to do is calculate the temperature at which this is the case using the delta H and delta S values that we already have. So we can rearrange this and say that T is going to be equal to delta H over delta S0 that we already have equals 128,900 joules per mole. Again, we got to make sure always that our units match up. 321.5 joules per K mole. And this will give us an answer of 401 Kelvin. So the idea is that, this reaction is endothermic, so it doesn't necessarily want to go because of the enthalpy change. It's uphill in energy, but it also produces gas. It also is favored by the entropy factor, and if you get it to a high enough temperature, the entropy factor takes over, and that temperature happens to be 401 Kelvin, which is what, 100 and some degrees Celsius, 130 something. It's not too bad. We're out of time, but do you want to just do a couple more? Just, I guess, are you saturated? How many more do you have? I see Samantha saying yes. Let's do them. You can leave if you want. Okay. These will be recorded and put online anyway, so whatever. What's the correct equilibrium constant for the following expression? This one is kind of a straightforward one. The equilibrium constant is going to be equal to, in fact, I'm just going to get rid of that for a second. First, let's look at the reaction. We have iron oxide solid plus 3 moles of hydrogen gas is in equilibrium with iron, just iron on its own solid, plus 3 gas phase waters. So in this particular equilibrium, we have 2 gases and 2 solids. Solids do not appear in the overall balanced equation because they have a defined activity of 1. So what we could say is that the K, and we're going to call this Kp because these are gases that we're dealing with, and we're going to express it in terms of pressures, is going to be equal to the pressure of H2O cubed, the 3 in front, divided by the pressure of H2 cubed, you see below. Solids don't appear. That's it. Great. How many more do I have? I got a couple more, but yeah, leave whenever you want. Solubility of silver chloride can be increased by dissolving it in a solution containing ammonia. So the first one is showing silver chloride in equilibrium with its ions with a super small KSP. Second one shows silver plus reacting with ammonia. So what that's doing is it's basically removing the Ag plus from the above equilibrium, causing that equilibrium to shift to the right. It wants to know what's the equilibrium constant for the overall reaction. This overall reaction is obtained simply by taking these two and adding them together. So that our K net here is simply just K1 times K2. 1.6 times 10 to the minus 10 times 1.5 times 10 to the 7. And that's 2.4 times 10 to the minus 3. No units, because it's a K, equilibrium constant. So that wasn't too bad. This one isn't a calculation-based one. It says, for the following equilibrium, what will cause the equilibrium to shift to the left? Right, so looking at that, we have gases. If you look at the number of moles of gas on the left, we have 2, and on the right, we have 3. So increasing the container volume will cause it to shift to the side with more moles, so that'll cause it to shift to the right. Removing some NO will also cause the equilibrium to shift to the right. Removing some Br2 will cause it to shift to the right. Adding more NOBr will also cause it to shift to the right. Decreasing the temperature, though, because this is an endothermic reaction where we can think of heat as being a reactant. If you decrease the temperature, it's like you're removing heat. That's going to cause this to shift to the left. 14 says, for the following equilibrium in a reaction vessel, which of one of these changes would cause the Br2 concentration to increase? So again, this is endothermic, just like the previous example. I mean, it is the previous example. Which will cause this to shift to the right? Well, lowering the temperature, no, that'll go to the left. Removing some NO will cause it to shift to the right and produce more Br2. Removing some NOBr will go to the left. Compressing the gas mixture into a smaller volume will cause this to shift towards the side of fewer moles, which is the left. Adding a catalyst has no effect on the position of an equilibrium. And so the answer here is going to be B. So if you can remove the NO as it's being generated, you can maximize your yield here of Br2. Okay, we have one more question. This is our last one. And this one is a little bit nasty, which is why I wanted to do this one in particular. We have our superscript problem here again. That is a 2 negative anion. We have copper 2 plus. Again, 2 plus should be superscripted. What will the concentration of cyanide be at equilibrium? Kc was 1.0 times 10 to the 25th. So looking at this number, this reaction by far favors the product side. It's saying initially we have 0.0120 moles of copper, 0.0400 moles of cyanide, and it's making this ion that we have here. So what we can do is kind of set up a bit of an ice situation. Where initially we are told that we have 0.0120 molar, 0.0400 molar, and 0. Change, this is going to shift to the right. In fact, it's going to shift hard to the right because of the very, very high equilibrium constant. This becomes minus x. This becomes minus 4x, and this becomes plus x. So at equilibrium, we have 0.0120 minus x, 0.0400 minus 4x, and this becomes x. Our equilibrium constant, K, is 10 to the 25th, and that's going to be equal to our product concentration, which is x, over 0.0120 minus x, times 0.0400 minus 4x, power of 4. Now this gets us into a very difficult situation, because look at this equation. We got x, we've got something times x, something minus 4x to the power of 4. This is going to give us a very complex polynomial. It's not a quadratic that you can just use the quadratic equation. It's not a cubic, even, where you could use the cubic equation. It's going to be there's going to be 5 terms. So I don't even know what you call that. It goes quadratic, cubic, quartic maybe, quintic. I don't know, is that a thing? We don't know how to solve those sorts of things, do we? It'd be fantastic if we could just say x was small and we could ignore it. Can't do that either, because look at the size of that equilibrium constant. That means x is going to be huge. It's going to go almost 100% to the right, so x also can't be ignored. So hypothetically, this is a solvable equation that you could run into a computer, but not one that you're going to do during a midterm, very, very easily. You're going to need a computer to tackle this. So are we stuck? Another way we can think about this problem, and the way I'm going to think about it is we're going to flip it. We're going to push this 100% to the right and then let it shift back to the left. Okay? Because this equilibrium constant is so high, okay, we know it's going to go essentially 100% to the right anyway. So let's think of it that way. Instead, we're going to push this 100% to the right, and if you look at it, cyanide is going to be our limiting reagent. So if we think initially, the cyanide is going to be 0, and then this becomes 0.0100 molar, we're left with some copper, 0.0020 molar. So this is looking at the reaction as if it's gone 100% to the right until you've run out of your limiting reagent. Then what we're going to let it do is then reach equilibrium from that point. So this becomes then plus x plus 4x minus x. That doesn't work because if x was really large, then you end up with negative concentrations in the bottom. So it turns out that x actually is going to be very close to the number you're subtracting it from. So they're like, the difference is going to be a very small number. So this becomes 0.002 plus x. This becomes 4x, and this becomes 0.0100 minus x. So the nice thing about this situation is we know x is going to be small in this case. Why is x going to be small? Well, x is going to be small because k is huge. It's going to be almost all towards the product side. So it's only going to shift back like a tiny bit. So what we can say here is if you look at this, we have k equals 10 to the 25. And that's going to be equal to our products, which is 0.0100 minus x, 0.002 plus x, 4x to the power of 4. And we're going to make the assumption then that this is 0.0100 over 0.0020 4x we can keep going here. This becomes 0.0100 over 0.512 x to the power of 4. Okay. So at this point, maybe to make things a little bit simpler, what we can say is if we take, if we kind of cross multiply here, we could say that 0.512 x to the 4 is 0.0100 divided by 10 to the 25. And that equals 10 to the minus 27. If you divide each side, I'm kind of running out of space here, but if we move up here, if you divide each side by 0.512, we get x to the 4 equals 1.95 times 10 to the minus 27. And now we can just take the fourth root. What do you call that? Not the cube root, the quartic root, or whatever you want to call that, of both sides. And you get x equals 2.1 times 10 to the minus 7 molar. All right. So x is a small number. The actual question says, what's the concentration of cyanide at equilibrium? Cyanide, you can see here, is going to be 4x. The concentration of cyanide at equilibrium, 4x equals 8.4 times 10 to the minus 7 molar. So this was sort of a, I'd say the most complicated sort of question we could maybe ask you about this sort of thing. This is well beyond what I would put on a midterm, but definitely there's some additional problem solving here where maybe the first approach or the standard approach, not that it won't work, it will work. It'll just create a real mathematical mess for you to have to deal with. So often a good strategy in questions like this, where you have like a either huge value of k or a small value of k, is to push it all the way to the side that it's going to favor and then inch it back from there, as opposed to the other approach, which is to start with all starting material. The other problem you get into, like k is such a huge number, 10 to the 25th, trying to do calculations in this sort of way can often like overrun your calculator. So I've run into this sort of problem many times before as well. I found a calculator that would solve this first equation online. And I put the numbers in, and it said like number too big or something like that. And I'm just like, well, that's not very helpful. So yeah, this method worked out pretty well. So thank you all for being patient with me today and going a little bit over, although I guess for prep, more practice is better than none. This will be recorded, it is being recorded, and I'll post this online as well. And everyone have a great weekend.